Hello, and welcome to another video lecture for ME and CE 501. In this video lecture, we are going to talk about impact loads, and we're going to learn how to model those and how to predict the effects given an impact load. But as we were finishing up class last time, we talked about having a 10-pound box or a box of a given weight and having it just barely out of contact with the table, and then letting go of that 10-pound box and seeing what the load on the table would be. And we decided that after a given time that the load on the table would be the 10 pounds. However, for a short duration, and we'll talk about what that duration is here in just a minute, for a short duration, the load produced by having this 10 pounds be loaded onto the table is significantly higher than just 10 pounds. And what actually happens is we model this as a forced, undamped, single degree of freedom system with a step input. So how this gets modeled is the table is a mass, the table top would be a mass, and the legs would be springs, and they may also consist of some mass. Then what happens is you have this spring and mass system, and you apply a sudden step load to that spring mass system. And when that happens, this becomes the governing differential equation of motion, where m is the original mass, x double dot is the acceleration of the original mass. So this would be, for example, the mass of the tabletop and the acceleration of the tabletop. The k would be the stiffness of the springs, and x is the displacement of the mass. And this p naught would be the 10 pounds or the step load. And you've seen this equation in 335. The solution to this equation turns out to come down here and be x is equal to p naught over k, where p naught's the applied load, or the 10 pounds, k's the stiffness, 1 minus cos omega nt. And this omega n is the natural frequency of the system, and t is the time. And we can see that there would be an omega nt such that the cosine of omega nt would turn out to be a -1. This omega nt, for example, would be 180 degrees. Then we'd get a cos of a -1 that would add a cos of a -1 that would add to this negative sign, so we'd end up getting a +2 here, and we would see that the displacement due to this added load would actually be twice the displacement as just given the load p naught over k. And as time gets big, this case actually doesn't show any damping. And so this model shows that we would repeatedly get that twice the load. But in real life, there's damping, which would absorb this and tend to make this damp out, and the vibrational effects would dissipate, and we'd end up with the 10 pounds on the table. So hopefully that makes a little bit more sense from our discussion. The bottom line then is, if we have this 10-pound weight right here and we hold it just barely above the table, let it go, the initial load could be up to twice the 10 pounds or 20 pounds, but that would happen for a short duration because of damping in the system that would damp out that vibration effect. These first two pages of slides are not in your textbook slides. I just brought them up and created them based on our discussion in class. So now we'll continue with the slides typically that we talk about in terms of impact loading. Most of this comes from a book on machine design by an author with the last name Juvenal. The The text is Fundamentals of Machine Component Design by Juvenal and Marshak. And in that section, he has a section on shock or impact loading. And impact loading has several different names. I just refer to it as shock, or it can be suddenly applied loads or impulsive loads. And there are many, many examples of this type of loading in the real world. Some examples are driving a nail with a hammer, dropping a weight onto a beam, an aircraft landing on a runway, a bullet firing. Lots of examples of impact loads. A car impacting another car, an airplane or a rocket separating a fuselage could be considered an impact load. So the idea of impact loads are that they are short duration, impulsive, and can be very significant loads in terms of magnitude. And the usual way for determining if a load is an impact load is based on some of the material properties and properties of the system. For example, if you have a really soft, flexible system compared to a very stiff system, an impact load or a given load over a specific amount of time would act differently on those two bodies. So as stated here, the usual way of determining if the load is an impact load is to compare the time over which the load is applied to the natural frequency or the natural period of the system that you're applying the load to. Now, the natural frequency, we remember, is the frequency at which a system wants to respond when hit with a load or an impact and then allowed to freely vibrate. And all systems vibrate when hit with an impact load. For example, a cantilever beam, if you hit it with a load, it's going to vibrate. The desk that you're sitting at right now, if you hit it with your hand, it's going to vibrate. The chair that you're sitting in, when you sit down in it, it impacts it and it's going to vibrate. A lot of these systems damp out and the vibration is reduced because of damping. But all systems will vibrate. And the natural frequency at which they vibrate is determined by the stiffness K and the mass M. And we take the square root of that to get the frequency of the system. And this omega is in terms of radians per second. And what we need to do is figure out the cycles per second and then figure out the time for one cycle. And that's what's done here. If we want to convert radians per second to cycles per second, we simply multiply by 2 pi. And 2 omega is equal to 2 pi f, where f would be in terms of cycles per second. And if we want to know the time for one period, or the time it takes for one cycle at the natural frequency, that's given by 2 pi times the square root of m over k. And this then has units of seconds. And so this would be the amount of time for the system to make one full cycle of vibration at its natural frequency. And the general rule of thumb is that if the load rise, so we apply the load, and if that load rise from initial application to maximum load is greater than 3 times the natural period, then the dynamic effects are negligible and the load can be treated as a simple static load. However, if the timing of the load is less than half a period, there is going to be an impact. So the example back here with our table coming in contact, or our block coming in contact with the table, that ramp up is nearly instant. And that's why this would be an impact load. But if we were to gradually and slowly let the weight fall onto the table and drop onto the table, and say it took 3 minutes for the full weight of the 10-pound box to come in contact and be on the table, this would not be an impact problem. But where we're holding it just above and we drop it, that is definitely an impact type problem. And so what we do is we compute this natural period and we find out how long that is in terms of seconds. Then we look at how long it takes our load to hit its maximum value. And again, if that's 3 times the natural period, it can be treated as a fully static load. If the time of loading is less than half a period, then it's definitely an impact. And the region that becomes a little gray is between half a period and 3 periods. And we often call that a quasi-static regime. And in that case, you would want to look at both situations. Some of the bad things about impact loads is they can be very destructive and they can be very large. We also know that impact loads can be tensile loads, they can be compressive loads, we can have bending stresses, torsional, and any combination of these loading types can be because of or due to an impact. The striking of a drill bit against a burr in terms of drilling a hole is an example of a torsional impact. Another example would be the hitting of ice or debris on an aircraft propeller blade. That could be a torsional impact. So there's lots of different types of impacts, and they can create all these different combinations of stresses. The main importance in design between static and impact loading is that the static load design, we focus on strength, and the members must be designed to carry the loads. But in impact loading, we're not so focused on strength, but we're focused on the system's ability to absorb energy. And it's important that the system be able to absorb that energy instead of have a super high strength. And energy is a function of the load and the displacement. And so if you have a very rigid material that is very stiff, when it sees a load, it's not going to deform very much. And if it doesn't deform very much, it's not going to absorb a lot of energy. And it will pass that energy on to other parts of the system, or for example, occupants in the system, and that's where impact loading can become dangerous. It's also noted that under impact loads, the yield and ultimate strengths of the material can be significantly increased. The load is applied so quickly that the material essentially doesn't have time to respond, and those values of ultimate and yield strengths can actually be quite a bit higher. So this kind of gives you a little bit of a background on impact loading. One of the main challenges with impact loading is determining this time over which the force is applied. And we'll call that the delta T. And we'll find out that that has a huge impact on the magnitude of the force, and it's also a pretty difficult quantity to determine. In impact analysis, there are generally 2 basic approaches to solving the problems. The first one is the wave approach. And when an impact hits a material and a force is rapidly applied to a body, there's the thin layer of material directly underneath the load starts to move, and a wave propagates throughout the undisturbed material. And as time goes on, that thin region of moving particles propagates outward into the body, and it causes an elastic deformation wave that causes the body to deform. And behind the front of that wave, the body and the particles are in motion. And these propagating waves then propagate out from the applied load. They hit boundaries and free ends, and then they reflect internally and vibrate back and forth. And the interaction of all of these waves can cause constructive and destructive interference. And you can actually produce regions of low force, but also regions of high force due to the interaction of the propagating waves. Classical theory on wave propagation can be used to calculate the stresses in these cases. However, these are really tough problems because the boundary conditions are not exact. Material damping is not completely understood. Changes in geometry and non-uniform loads all make wave propagation methods pretty difficult. Because of the difficulty with and challenges with solving the wave propagation methods, tables and lookup charts have been developed to help us use those, but these methods are typically not used in practice, and other easier methods are used. However, in the wave propagation approach, what essentially you have is the stress is equal to this quantity here, where this V is the striking velocity, E is the modulus of elasticity, and this rho is the mass density of the material. And what we end up getting is we get a maximum stress then that is equal to this original stress, sigma naught, or nominal stress, we could call it, multiplied by R. And R is a ratio that lets us compute or determine the maximum stress. And it's simply called the stress ratio. And you can go to this table, this book by Roy Craig, Mechanics, and see a table that gives R values for various situations. We're not going to use that approach too much. We're going to come back and use an energy-based approach. We get reasonably good answers with the energy-based approach, and it's a lot more practical. And this is what you'll use to solve problems when you're in industry and when you're in the working world. The idea behind this is based on conservation of energy. So for example, if we have a weight W that is above a cantilever beam by a distance h, we can model this cantilever beam as a spring. And we can actually compute the stiffness of this cantilever beam spring. You can do that by knowing the static deflection. So the static deflection of a cantilever with an end load is PL cubed over 3EI, where this P would be the same as this W. And we know the basic equation F equals Kx, where F is the force, K is the stiffness, and X is the deflection. If we rearrange this equation here for the deflection of a cantilever beam into this form of the equation, where we have the force equal to the stiffness equal to the deflection, we get that the force P is equal to 3EI over L cubed times the deflection. And so the stiffness for this cantilever beam is 3EI over L cubed. And the beam mass and damping can also be accounted for in this model. And you talk about that if you take ME 535, mechanical vibrations. But for for this approach here, we're going to just use this and assume that we can get the stiffness of this cantilever beam by 3EI over L cubed. Now we want to kind of look at the energy in this system up here. If the maximum deflection of the spring up here is delta, and the total drop height of the mass is h, then this weight W falls a total distance of h plus delta. And the loss of potential energy would be the mgh type of term, where h would be h plus delta. And so we would have W, which is the mg, plus the height, or the drop, h plus delta. And the resulting increase in potential energy of the spring, or of the system, is 1/2 k delta squared. And we know that back from spring mechanics, where the energy stored in a spring is 1/2 k delta squared. So we can now set those two equations equal to each other, as shown here. And rearranging, we get this quadratic in terms of delta, and solving this using the quadratic formula, we get this equation here. The maximum deflection would be obtained by using the plus sign. And so the static deflection of the beam is given by W over K. So if we wanted to know what the static deflection of this beam was, what we would do is we'd let W come in rest here, and that W would be given here, and then we could apply the stiffness and find out that static deflection. And that's given here then. We can write that as W over K plus the W over K times 1 plus 2HK over W square rooted. So this expression for delta, if we have H equal to 0, so no drop height, we can see is W over K plus W over K, which is 2 times the weight divided by the stiffness. And that's what we just talked about at the beginning of this section, was that if the weight was just in contact and let go, we would actually get twice the deflection, or see twice the force. And this tells us the exact same thing. It's interesting to note that this is a very strong function of h, so the bigger h, you can even start to see significantly greater force magnitudes than twice, 3 times, and so on. We can look at this deflection equation and change it to force simply by multiplying both sides by k, and doing that, then we get the force is equal to W plus W, and so on. But it's the same equation as this deflection equation. Now, this term up here that's in the parentheses is called the impact factor. And it's the factor by which the force is increased due to the impact. And it's the force that is caused by the dynamic excitation versus the statically applied load. And here again, note that if h is equal to 0, then we get the factor of 2. So for a uniform bar with a load striking the end, the stress and deflection equations can be expressed as shown down here. And this A is the cross-sectional area, L is the length of the beam. And note that we have Y is equal to deflection here. And so we can compute sigma max is given by this equation, and the deflection, the maximum Y, is given by this expression. And the assumptions associated then with this energy approach are that the mass of the body is much smaller than the striking mass. So in our spring mass system, the original mass is small. The deflection of the body is directly proportional to the applied force and is not a function of time. So the deflection of the body is proportional to the applied load, which means that it is directly related, the force goes up, the deflections go up, and it's not a function of time. The material remains in the elastic region and obeys Hooke's law, sigma equals EE. And there's conservation of energy. There's no energy lost during the impact, which means there's no damping in the system that's accounted for immediately. If the weight of the bar is not negligible, then these equations up here need to include that weight of the bar, and you can see we get these additional terms down in here, where this little q would be the weight per unit length. And so these equations become a little more complex if the weight of the bar is not negligible. Here's kind of an interesting example. To maximize the resistance of a machine or structural members to impact loading, it is important to distribute the maximum stress as uniformly as possible. So let's look at what I mean by that statement. Here we have a rod with area 1 and length L. Over here in this case, I have the same length of a rod, so the overall length is exactly the same. I have a length of this rod in the middle that's a third of the length that has the same A1 over here. Then the two ends of this rod have twice the area of A1. So they're much bigger in diameter. There's more material by far in this model than there is in this model. So these columns have the overall same length and the same minimum cross-sectional area. They are made of the exact same material, and we're going to neglect effects of the stress concentrations due to these sharp corners. Now let's look at this. The right column has two regions where the cross-sectional area is twice the minor cross-sectional area. So here and here we have twice the area. Under static loading, so under a steady static load, slowly applied load, the force required to produce first yielding is given by F yield equals A times Sy. And this is just Sy equals F over A, or the stress equals F over A, and we set the stress equal to the yield strength. So this is what you've seen before. Now, the total strain energy over here in bar A, in this bar at the time of first yielding, can be written as the average force times by the deflection. So the average force would be F max over 2 multiplied by the deflection. And when we propagate this in terms of stress, we can see that this turns out to be Sy squared over 2E times A1L. Now, in calculating the total strain energy for bar B, it must be recognized that the stress level in the two end segments is lower than the stress in the central segment by a ratio of A1 over A2. So we know simply by applying a load to this member here, the stress in this region and the stress in this region will be smaller than the stress in this region. Okay? So using that, we can write the strain energy for bar B in a piecewise fashion and get this result here, where we have the strain energy for the middle member. Our length is now changed to L over 3, and then we have the strain energy of the two thicker members. And letting the ratio of areas be this factor of 2, the strain energy in rod B can be written as 2/3 of the strain energy in rod A. So what this means is that the energy stored in the bar B when yielding begins is only 2/3 of the energy stored in bar A when yielding begins. So bar B will actually begin to yield with a lower strain energy than will bar A. And so the impact resistance of design A, with its smaller total volume, is significantly better than the impact resistance of design B. So furthermore, if the stress concentration factors have been considered, design B would have even been worse. Now note, however, that if the whole area of bar B would have been 2A1, then the impact resistance for bar B would have been higher because you have more material and the stress would have been uniformly distributed. But based on these two systems right here, if you were to design these two systems to carry an impact load, this system here would be a better, more capable system for carrying an high impact load and absorbing energy than this system here by a ratio of 1 to 2/3, which is significant. So the key to designing members for maximum resistance to impact loading is to make sure that the maximum stress is uniformly distributed throughout the largest possible volume of the material. And so certainly making this bar bigger over here would help reduce the impact resistance. But by doing it like this actually reduces the impact resistance. The goal is to distribute the maximum stress over a larger area. Grooves and notches greatly reduce impact resistance because they are small volumes of highly stressed material and they have low energy absorption. So a relatively minor impact may cause fracture in a member that contains holes and fillets because of these stress concentrations that prevent the system from properly or from maximizing the energy absorption ability. Threaded joints, for example, can also be particularly bad in impact loading. Let's look at another example. This is impact loading on a beam. This is a simply supported steel beam, so it's simply supported on each end. It's 60 inches long, and it has a rectangular cross section 1 inch wide by 3 inches deep. And we're going to take a 78-pound weight, and we're going to drop it from a height H and drop it at the midspan of the beam. If the yield strength of the material is assumed to be 40,000 psi, and if the beam mass is neglected, we want to find out what drop height would be required to produce first evidence of yielding in the beam, and what is the impact factor under these conditions. So the first thing we want to do is come up with a stiffness for the beam and then apply that to find out the strain energy and compare that strain energy to what it would be at failure. So for a simply supported beam with a point load in the middle at the midspan, the static deflection is given by WL cubed over 48 EI, where the W is the point load. The maximum bending stress is at this midpoint, and it is computed by MC over I, where M would be force times distance, W over 2, L over 2, and so we get a maximum bending stress at WLC over 4I. And now to determine the maximum deflection, we can come down here and compute the deflection based on our stress equation, and we get deflection is max sigma L squared over 12 EC. So again, we simply expanded the delta static or the static deflection equation to where we could absorb sigma max and then see what was left in the expression. And when we do that, this is easier to do when you have an axial rod like we did before. Here we have a bending case, and so our equations 1 and 2 here can be used to write our strain energy. And writing our strain energy for this beam, we get sigma max squared IL over 6EC squared. And so this is the strain energy in the beam due to dropping the weight on the beam. And I won't expect you to come up with these strain energy equations, but we ought to have a feel for where they come from and how they're derived and developed. Now, the drop height energy is given by W or mgh, where we'd have W and then this would be our H term. And we know our delta max then is given by the equation we just computed on the previous page. And so now we're going to set the strain energy in the beam equal to the drop strain energy, and we're going to solve for the maximum stress. And that becomes this expression right here, real similar to the expressions we looked at earlier on. Now, using the given numerical values in this problem, we can compute the sigma max as given by this expression here. And if we set this then equal to the yield strength, we can solve for H, and we get that H is equal to 6.5 inches. So what that means is that the 78-pound weight, if dropped at 6.57 inches, would produce initial yielding in the beam as it was dropped. And the impact factor for this case is huge. Look at the impact factor. By dropping that weight 6.57 inches, it turns out to be an impact factor of 51.3, or 51.3 times what it would be without dropping, or without a drop height and just the applied load. So 51.3 times what the static load of that 78-pound weight would be. That's a huge effect by a simple drop of 6.57 inches. I hope that brings into mind and helps you realize how critical drop height is and how significantly it can change the impact force and give you this impact factor that can be really high due to relatively small drop heights. It's kind of important to understand the difference in the results between an energy-based method and the wave method. So we just looked at the energy-based methods. The wave method was the challenging one we talked about early on, where you have wave propagation. This system, and this page here, kind of shows us the difference between the results that we get from the two methods. And so what we're seeing here is we're seeing this moving weight W that impacts the end of a bar. And then there's a compression wave that travels and propagates along this bar. This happens to be a well understood wave propagation problem, so we can actually get a wave propagation solution because it's a rod with a traveling wave in kind of one direction along the length of the rod. The maximum stress can be several times the initial impact stress, and that's what we'll see below. In this figure, the V right here represents the velocity before impact, and VA represents the velocity after impact. And the exact analysis, which is based on the wave approach, and it's very challenging, gives us a solution that we can obtain. The stress in the bar due to the energy-based approach is given by this equation here, where we have the velocity, we have the cross-sectional area, we have the stiffness, we have the weight of the beam or the rod. This is acceleration of gravity, and then W's the weight of the impact. So what we see here is that the energy stress, or the stress in the bar due to the energy method, gives us this equation, and this can be a big function of W over WB. If we relate this stress due to the energy method to the exact method, this sigma naught, we get this relationship here, or this factor. And if we look at what happens if the W, or the weight of the impacting body, is the same weight as the beam or the rod, we'd get 1 here, we'd get 1 over 2 here, so we'd get the square root of 1/2, and we would see then that the original energy, or the impact stress based on sigma E, is significantly different than the energy based on the wave approach. So if we look at this, the same ratio developed based on the wave approach is difficult, but an empirical equation gives us this. And if we look at this plot on the next page, we can see that there's a big difference between these two approaches. So note that unless the striking weight is many, many times greater than the weight of the struck bar, the energy method can give really low results, and you can get significant errors. But if the weight of the striking mass is smaller, then the reverse will also happen. So you need to be really careful with systems where, unless the striking weight is many times greater than the weight of the bar, then the energy method can be really low. So be careful with that when you're considering using the exact versus the energy-based approaches. However, in most systems, that is the case, and the energy method gives a very good result that can be relied upon, and certainly a good approximation for design and analysis. We're not going to talk about the short duration impulse. We're going to go ahead and finish our discussion on impact loading at this point. Thanks for watching.